We're on.
Okay, so it's a great pleasure to introduce Chris Sangwin, whom I've known for rather over 25 years, I think. Jeremy remarked I'd done too much administration. I knew Chris when I was head of mathematics, as a research student in mathematics, who's gone on and we published together on questions about actually looking at the foundations of mathematics, not in the sense of what we normally think of, the foundations of them as we actually learn the subject. I think that's a very important question, but we perhaps haven't looked at enough. So, Chris, over to you.
Thank you very much, James. So, my name is Chris Sangwin, and I'm a member of staff in the mathematics department at the University of Edinburgh. And my primary interest is mathematics education. And so this is going to be a talk primarily about learning mathematics, and one particular topic about learning elementary mathematics and learning algebraic reasoning. Something I'm going to call reasoning by equivalence, something I'm sure you're all familiar with. And in particular, I am interested in the extent to which we can automate the assessment of students' work.
Something I think we can all sign up to.
Right. I have marked 500 scripts of Introduction to the Algebra in December. Yeah, absolutely. So I'm going to answer that question: is what can we do today? What can we do tomorrow? And I'm going to show you some software that will be going live very soon. And I'm very close to finishing the testing for that. And then a little bit more speculative and an appeal to you folks in the theorem proving community for some help in what we might do ever. Well, why might I want to do this? Let's just get that out. Get that to answer that question. Well, if you want to become an expert in anything, you need to practice it. And so online assessment is very valuable to our students in giving them practice, repeated practice. Classes at university are large. So I have more than 500 students in my classes. So if I'm going to we have a team of 35 tutors. So that's a lot of staff time devoted to hand marking. You all know this. I put also that the internet distributes. It distributes information, it distributes communication, and so on. Actually, some of the evidence on technology education suggests that it increases the social divide, it doesn't decrease it. So we have to be a bit careful how we deploy education, because people who come from well-educated families are shown how to use a technology that makes them better, and then a load of other people are left behind. Just having more information in the world doesn't necessarily reduce the social divide. So that's what I mean by that. So there's just a caution there. As a researcher, I have this sort of constructivist view. If I can automate something, I've gained a particular understanding of it. So I want to solve an equation. If I can write a program that will solve that equation, then I've learned something about how to solve those equations. It's a very pragmatic view. I got bored of solving Sudokus, I wrote a program to solve Sudokus. If I can automate the assessment process, I will learn something interesting about assessment through that research goal of automating the assessment process. I don't think repetitive work, such as marking, is a sensible use of an expert, and I include our PhD students in that. So let me show you the typical thing that's absolutely standard in maths. So here's an online assessment system. Let's just get this wrong, x minus 6, 4. So, sorry, I haven't got that right. So there is some expression. The student is asked to find the solution to some randomly generated problem. This is entirely elementary calculus. Nothing deep about this. Entirely mechanical. Not defending this as a question. But there you go. There's some validation things. So this is my software. It's widely used. And one of the distinguishing features in this software is that I have separated carefully a concept called validity from a concept called correctness. Okay, that's actually a key feature. Students are apt to type in 0.33 when they meant 1/3, and we want them to type in 1/3. A, because that's correct, and 0.33 is not correct. And secondly, it means the whole marking procedure becomes much more robust. Right? And students are not, therefore, penalised on a technicality. So let's just go back to x to the power 4 here and mark it and see what happens. So incorrect answer, the derivative of your answer should be equal to the expression that you're asked to integrate. That was blah. In fact, the derivative of your answer was respect to x is this, so you must have done something wrong. So behind this is Maxima, the computer algebra system. It takes the student's expression, it establishes objective properties of the student's expression relevant to the question, and on the basis of establishing or otherwise those properties, it gives them feedback and other outcomes like numerical marks and other stuff. Okay, that's the sort of, does that make sense, what it's doing? Dealing with the fun.
You only have 10 goes, is that what we're
Yeah, pretty much, yeah. Because actually our experience is that if a student doesn't really get it in 3 goes, they're better coming and talking to an adult. And it's actually not in the student's interest to sit there for hours guessing and checking and guessing and checking. So there are reasons why we would want to stop certain behaviours, because it's not helpful to the student. Yeah, absolutely. This is all fully controllable by the teacher. What you do in your class is your responsibility. Okay, so it's very flexible. Some people actually don't show marks at all. And there's some research evidence that not showing numerical marks is much more helpful. Actually, students focus on the marks and not on the feedback. So there's all sorts of things like that. Does that just give you a sense of what the current state of the art is in this sort of area? So, typical features. Oh, so the difference in this is the feedback, which is about the meaning, and the feedback up here is about validation. Validation feedback is always available. So even in a timed exam, they will get the validation feedback, so students are much less likely to be penalised on a technicality, whereas they won't get this feedback until after the exam, for example. So that separating these things out really makes a big difference in practice. Right. So we generate random structured questions, typically by starting with the answer and reverse engineering it. If you want to ask the student to factorise a quadratic, you don't start with coefficients, you start with the roots. You've got maxima there, so you start with the roots and expand it out and set that as the question. Kind of obvious. The answer contains mathematical content. This is not a multiple choice game. You establish objective mathematical properties of the answer. So typically there will be 2 properties that you want to establish. One, that it's algebraically equivalent to the correct answer, and 2, that it's written in some kind of sensible, appropriate, conventional form. And those are separate properties, and you establish them separately. Right? So in many situations you will establish a whole wide range of properties that are relevant. You can also establish that the student's answer is consistent with a common mistake, so, and give them helpful feedback. So the feedback and outcomes are all stored. So formative feedback might be telling them how to improve on the task. Summative feedback might be a numerical mark, and then there will be some statistical analysis, internal statistical analysis. Okay, so my system is designed with higher education in mind, but there are loads of these systems around. WebWork is very big in the States. If you've seen that, it's a very similar goal. There are a whole range of these. And a few years ago, I wrote this book about this endeavour, Computer-Aided Assessment of Maths, and it contains a thorough review of people who've been doing this kind of thing from the 1960s up until I wrote the book. A lot's happened in the last 4 years, as you'd expect, but if anyone's interested in this area, there are a lot of references in there which I wish I'd had a long time ago when I started this out. Okay, so yeah, so here we are. Okay, so there we go, that's the current system, and this is the sort of feedback that you can get. Write this in factored form, and the system says it's not factored. You could still do some more work on this term. Right, so that's the kind of specific feedback. Any questions about at this stage as to where I've got to?
The student can type something in which is, as it were, not in normal form. How clever is the system at seeing whether their answer is equal to the right answer?
One of the things I've realised is that teachers make a lot of judgments very quickly, and you have to encode those. But there aren't very many different classes of judgments. So one of them is it algebraically equivalent? And then the next most useful thing to decide whether it's the right form is to use equivalence up to commutativity and associativity of the operators. So if you've typed x plus y and I've typed y plus x, it will just condone that because within that equivalence class, commutativity is included. Yeah. But if you've written x plus x and I've written 2x, that's using the additive property of plus. So ours would be different equivalence classes under that.
And if in the previous thing, if I'd written, I don't know, a divided by 4a times x plus 1 to the fourth, it wouldn't accept that.
So I didn't hear what you said, sorry.
Well, I mean, I include some spurious extra thing that on the top and the bottom line, as it were, in a fraction.
Depends what I programmed in that question. It probably would accept that. So what it would do there, right, should we have a go? I know what it'll do there.
Sorry, I'm diverting you from
No, this is Something like that?
Something like that, say, yeah.
Okay. Let's just get it over. Oh, I've lost my internet connection.
You could have it A over 4A would be even better.
Okay. Something like that. Probably, I hope it's going to complain. Okay, so
yeah, right.
so it is doing that, but it knows that the constant that it knows that the constant integration. So that's probably not ideal. I mean, what I actually typically find is that to get these to be super reliable is a 3-year cycle. So year one, you make sure the correct answer is marked correctly and everything else is marked incorrectly, and then you actually look at what students do in practice, and mostly they do sensible things because we have.
It's only correct if I is non-zero.
Sorry?
It's only correct if I is non-zero.
Yeah,
that's
I
actually
want you
good.
to press check and see what happens.
Oh, okay. Yeah, that is the feedback. Right, the A non-zero is actually going to be a big theme for the rest of my talk. So on that note, let's get back to the talk. Okay.
Quite clever though.
Sorry?
That was good. I'd forgotten about the constant of integration.
Right. Well, thank you for admitting that. Right, so a calculation is some deliberate process that transforms an input to an output. Reasoning is something perhaps a little bit less well specified. And so the whole definition here, we're using a computer. By definition, we must perform some calculation. So the question becomes, what forms of proof can be reduced to a calculation? Okay. For you folks in this audience, that's sort of obvious, isn't it? I'm going to take a proof from a student. To what extent can checking that become a calculation? And there's one particular form of calculation which is a natural extension of what I've done so far, and that is working line by line. So this is an International Baccalaureate sample question, absolutely standard kind of elementary pure maths. Solve this equation. The student has to solve log to the base 3 of x plus 17 minus 2 is log to the base 3 of 2x. So I've got some domain constraints here to satisfy your division by 0 business. And then you reason by manipulating it algebraically, and you end up with the complete and correct solution x equals 1 at the end. Okay, so that's and so this is a single entity. So from an educational perspective, I think it would be unusual, it would be more usual to think of this as a collection of equations rather than a single sentence, a single long English sentence. Okay? So that's what I mean by reasoning by equivalence, and it's ubiquitous. It's really important in education. It's a natural progression in number and algebra. It's the start of proof and rigour, actually, because certainly in the UK we have no deductive geometry, and so we don't teach proof via Euclid, although actually I think often 100 years ago Euclid would have been a memorisation test, actually. If you look at the exam papers, it says state and prove whatever proposition from Euclid, and you just have to remember it. Right, so whether that was ever really a deduction test, I don't know. But it's certainly the start of proof and rigour in current school maths. It involves multi-step calculations. Students have to take responsibility for their work and see a calculation through. So they've actually got to link together many steps. They've got to make strategic decisions about form and where to go, and they've got to then reason about the answer. So I know from the perspective of an expert mathematician or computer science, this is terribly elementary, but this is where it all starts. There is more logical reasoning in this reasoning by equivalence than simply working line by line. There is implications and so on. We'll come and see that. And it's also included in many other methods. So further on in mathematics, this is just standard steps. So proof by induction, many proofs by induction. If you're trying to prove that the sum of the integers is half n plus 1, then a lot of that proof is this reasoning by equivalence. You start with p of n, you add n plus 1 to each side, and you rearrange the formula and so on. This is reasoning by equivalence. So this is included in many other processes. And in particular, I was teaching real analysis at the University of Birmingham for many years, and students would mostly get the template for the proof right, but many students would struggle to manipulate inequalities with absolute value signs in them. Right? So that is included in reasoning by equivalence. It's basically being able to string together a bunch of correct algebraic steps. Right? And so that was actually holding them up. And we then end up spending hours condoning, doing the follow-through marking and condoning all this stuff because it's not And actually in school mathematics, this is the primary form of reasoning. So I did an examination of IB papers. So this is published in Computers in Education. And I did a thorough analysis of the extent to which international baccalaureate maths papers can be automatically marked. Okay, that was the research question. What percentage of the marks currently awarded can I award automatically? And that's when I really paid attention to the reasoning by equivalence.
Not religious education, as one might think, our Eastern.
I hadn't even thought of that. So, yes. So 1/3 of the marks currently awarded by international baccalaureate papers are for this process. It really is the primary thing. And actually, when they have reasoning marks, they call these method marks. They don't call them reasoning marks. They have a separate classification for reasoning. And that was 4%. And that was for things like the second derivative is strictly negative, and therefore we can infer something about the nature of stations.
What is exactly IB?
International Baccalaureate is an exam system taken aged 18 internationally. It's equivalent, it's very similar to the UK A-level, and actually internationally there is this very stable, very similar mathematical core which includes algebra of polynomials up to cubics, some rational functions including some partial fractions, formal differentiation, symbolic integration, solution of equations, some trig, all those core pure mathematical parts. Whether or not complex numbers are included in that is sort of a bar. UK A-level does not include complex numbers, for example. So this is the exam systems taken by most people around age 18.
How big is the core? How many exams you had to go through to get this 1/3 number?
I went through, I'm happy to send you the paper, but I went through a lot of questions, right? A large sample of IB questions.
So you took a random sample of it, basically?
Yeah.
Oh.
Representative sample of IB questions.
Is that all like written somewhere in LaTeX or?
Yeah, I published this as a research paper.
But the full core is available also for?
They're not in LaTeX, they're available as Word documents. So.
Oh.
How do you subdivide along with various grades of math?
Yeah, we went through them line by hand, and we made.
Yes, but it might be biased if you were mostly standard level or mostly advanced.
It was a representative sample. It was a representative sample of the IB questions currently taken. I mean, you want to look at the methodology, we can do that.
No, I'm just interested in the size of that, just a big data question, basically.
Oh, it wasn't massive data, it was done by hand, it was it's a sample. And this is why I've reported it as 1/3, right? I mean, I'm confident that somewhere between 25 and 35 to 40% of the marks are awarded for this, yeah? But basically, it's the most important single thing in school level maths.
Right, 0.33.
Yeah, with some error bars on probably, if I was being a good physicist. So that's the importance of it. So this business of turning reasoning into calculation has a long history. This is Leibniz, who asked for a universal scientific language which would enable us to judge immediately whether propositions presented to us are proved with the guidance of symbols alone by a sure and truly analytical method. That's his famous quote. It continues with Bull, whose laws of thought. He wanted to reduce logical reasoning to an algebraic equation. And actually, this is the earliest example of English algebra that uses reasoning by equivalence and that tries to set out an entire algebraic argument as a single object in a formal way. It's Pell, 1668. He has his problem. There be three numbers in continual proportion. Their sum is 74 and the sum of their squares is 1924. So A, B and C are the unknowns. Lines 1, 2 and 3. A plus B is 74. Their sum is 74. The sum of their squares is this and they're in continual proportion. So A to B is the same as B to C. Okay?
Wouldn't know what continual proportion meant unless he'd written down.
Right. Okay, so step one is formalise your statement of your theorem to prove, or whatever it is. And then he goes through this line by line, and here he is subtracting, this is very hard to see, I'm sorry it's such a poor quality slide, but he's subtracting from line 1, line 2. So it's got line 1, or is he adding? He's adding, no, he's adding 2 lots of line 2 to line 1. Okay, so that's what he's doing, and he just works through it line by line. He's not using a squared because exponential notation was still not common at that point. The way symbolism has evolved and the way that we understand maths through symbolism and the way that we mix symbolism and rhetoric is an interesting part of this whole education story. Okay, but this is the earliest example I know of. I'm pretty sure this is the first example anyway.
So how did it go from 1,900 to 5,000?
He squared the I plus B plus C.
I got this wrong?
He squared the first equation.
Oh, he's square.
Okay.
And took the second.
Oh yeah, sorry, that's absolutely yes. The 1, 2 with a circle around it is squaring.
Oh,
That's
right,
right.
yeah,
That's
yeah,
right.
So it's not by equivalence.
Right, we'll come on to that. Yes, that's, God, you're way ahead of me. Right, so the goal, what is my goal? My goal is to develop and assess some reasoning by equivalence. That seems like a pragmatic next step for my online assessment system. It's a valuable thing to do, and it uses the equivalence checking that my system is particularly strong at. Okay, so it seems like and I'm not an expert in automatic theorem proving, that's not my background. Tomorrow, maybe we should incorporate some proof system features, and in the longer term, some proof checker. I really don't want to be marking these proofs when they can be marked automatically. All right, so I'll show you what my current software looks like. I hope this works. Let's try this again. This is on my local machine. If I re-attempt the quiz. Good. Let's go to 3. So this is the current interface. It's part of Moodle if you used any of those long online learning systems. And so what should we do? X minus 3 squared. I better take away 9 is 16. So it works line by line. I've done that wrong. Yeah, I got that wrong. It's squared. And so you work line by line and you just type in your equations. And the system is telling you here that it thinks that that equation is equivalent to the previous one. And then at some point you would say x minus 3 is plus or minus 25, so x, oh no, plus or minus 5, so x is 8 or x minus 5, so that's going to be minus 2. Or you might, if you're a student, you'll just write that, won't you?
Would you get full marks if you didn't have the 2 middle steps?
Oh, that's a good question. Right. So, I mean, just this is an invalidity, and from experience, I know that's something students are likely to do. So we just tell them what to do. But I'm not going to condone that. It's a decision I've made. I've made lots of decisions. Right? You can see I've made lots of decisions here, and we'll see whether these are decisions that are helpful to the students or not. But I want my students to learn about binding powers, and I want my students to learn about communicating with the machine. And so here I can check, and I can just say, this is the way you have to type it in. And it does sort of irritate them that they then have to actually change it, but that's the design decision. Okay, you'll notice that this says solved by factoring, so that's now valid. So it's wrong. Okay. Even though it's a perfectly reasonable piece of reasoning, there will be a whole bunch of properties that make this answer correct or incorrect. One is that every line is a sensible next line. Right. We'll discuss what that is. One is that you started with the right equation. No point starting with the wrong equation. Right? I mean, you've got to make this robust that what the students are likely to do. They're going to do all these things, okay? And you don't want to penalise people on technicality. It's just horrible. How many lines do you have to have in your argument? You have to end your argument in the right place, and in this case I have decided that I want to see the factored form somewhere. Right? That's what makes a solution correct. So the teacher has to decide. You are responsible for your own class, what happens in your class. You have to decide what properties constitute a correct or incorrect solution. Okay? So you may have too many steps, or you may have too few steps, or that's up to you. Okay? Another design decision here is that I have immediately given them some feedback here. So this is kind of a proof checker as you're going along. I haven't delayed this until the end, where that might be something that you want to delay till the end. Okay, that is also a choice in the system, but for the purposes of illustration today, I turned it on in the validation feedback and not left it to the correctness feedback. I mean, I think it's pretty important. So it would depend on the student. Okay, so the equivalence class of expression is defined by the solution set. So I'm working over some variety. That's the way it works. Come back to that. What does it mean to solve an equation? So solving an equation is a progressive transformation which within representatives of that equivalence class that ends in a certain form. So it ends in the form x equals something or x equals something else. That's what solving an equation is. Okay. So if you've got an equation of a circle, you might just leave it as x squared plus y squared equals r squared because it's ended in a certain form. You're not going to turn that into y is plus or minus root, whatever. So it's about part of the game in maths and learning maths is knowing what those conventional forms are. In my example, I told you what form to use, but that might be something that students should know. Right, so how do students go about actually solving these equations? I did some research and I had 147 students answer these two basic algebraic problems. They were not maths majors, but they had better grades than the maths majors. They were engineering students on a very high status engineering program. So they all had the very best grades you could get in maths in this country, and most of them had further maths as well, which is so 85,000 people a year do A-level maths, and about 15,000 people also do further maths. So it is a very high status qualification for those people that don't know. And this is what the result. Does anyone want to suggest what the students did? Guess? No, okay. Only 10% of them showed any evidence of writing logical connectives. So they just write disconnected equations. Okay, so that's fair enough. Is that sort of typical students do? Only 2 students checked that their answer actually satisfied the original equation. And only 1 student considered domains of definition in this equation. Very similar story for the second one, although they found it harder. Only 60% of students finished this problem by getting to those 2 solutions. And only 16% of the cohort also eliminated one of them because it doesn't satisfy the first equation, which is more than here. And again, not really showing any evidence of connecting together equations by logic or any other checking of domains. There are some domain things here, for example, which allows you to eliminate one of those solutions. Now, I am not the first person to moan about students, okay? And I'm not here to moan about students because this is my predecessor in Edinburgh. There are few parts of algebra more important than the logic of the derivation equations, and few unhappily that are treated in a more slovenly fashion in elementary teaching. I don't think it's very helpful for university people to just moan about teachers and students at school, and I don't want to get into that game. Crystal's algebra textbook was extremely influential. He was a very thoughtful colleague, academic. It's still in print, his book on algebra, and as far as I can tell, it is the first UK school textbook to include Argand diagrams. So in the 1800s, there's all the work by Cauchy and Riemann on the complex analysis, but it took 50 years to get any of that into school level work. At the beginning of the 1800s, people are advising students to ignore these fictitious quantities. It just takes a long time for stuff to get into the educational system in any meaningful way. So let's look at how you could solve the first of these equations with computer algebra system, maxima. So you type in the equation into maxima, and then you rationally simplify both sides of the equation, and then you multiply out, and then you notice you have a common factor, so you divide by it, and you end up at the contradiction 13 equals 7. That's why I put this problem on my problem sheet. Actually, almost none of the students fell into this trap because they multiplied out the brackets at this stage. They multiplied out both sides before subtracting. And I have to say, personally, I'm disappointed the software allows me to behave like this. I mean, I think that's actually, I'm not criticising the people who wrote Maxima. Some of you may be here, I don't know. Because this is old software and it's first generation computer algebra system, but good design should help you not fall into traps like this. The only solution to this equation is x equals 10. So that shouldn't, we should be designing things to help us avoid this problem. So that leads on to this question, okay? To what extent do I want to automate current practice? Because if I do something radical, no one will use it. Right. And I'll show you what radical means in educational context. This is a suggestion by Margaret Brown. And she is an extremely thoughtful maths educator. She was at King's. Is she retired now? I think she's retired now. Yeah.
Okay. Can I ask you a question about question number 2? Did you try doing that? Like the system and see what happened?
Yeah, you just square both sides and it happily gives you the two solutions.
Obviously,
If you work line by line in this way. And what I didn't say is the system encourages you to work line by line because the percentage sign means use the previous line. It's designed to do this. It's encouraging you to do that. Okay, so this is Margaret's suggestion. Inspired by computer notation, on an old computer you had to type the up arrow for exponentiation. She said write logarithms as subscripts. Okay? So it's not that, you would not think this is a hugely radical suggestion. If you've got exponentiation for superscript exponentiation, so you know, the natural logarithms, it becomes x, e sub x. So if you want to, right, so which of the following are true? Oh, so to solve this equation, we just push everything down, don't we, basically? You just push everything down and then you go down and you come back up so you get to where you started, so x is log to the base a of b. Right. In fact, algebraic symbolism is precisely designed to do this kind of salience, visual salience it's called, where the laws of algebraic manipulation are visual in nature. So, people have been more or less explicit about that when they've designed notation in the past. Okay. So which of the following are true? They're all quite appealing, aren't they? You know, you sort of cancel, you add a C in here and you cancel the B. I'm not worried about domains, right? That's a different story, of course. And how would you write the change of basis formula? So I'm saying, you know, once something's fixed in your mind, it's really hard to change it. So if I could trivially write logarithms in my system by typesetting them that way. We can use the underscore character to enter them. You can parse that. I think that would be too radical. I don't think anyone would use the system if I did that. Which also means, I think, if you're designing something new, you better get it right first time because it's going to stick around. Can we use reasoning by equivalence more? And I said it's already 1/3 of the reasoning. But actually, I think there's scope for, if we really accept this as an important activity, for using it more than we do. So here is a question from, this is from a Finland, a final exam, age 18 in Finland. I stole this one from. For what values of A, find the values of A for which this is negative for all x. So I think a typical way most people go about this now is to appeal to the intermediate value theorem, to solve the quadratic equation and then appeal to the continuity of the graph and say, reason that way. So you're using higher theorems. But actually you can do nearly all of it by reasoning by equivalence. If you gather your terms and complete the square here, and then you put one sentence in, this inequality is required to be true for all x. It must be true when the right-hand side takes its minimum value. This happens for x to the half. So it's clear where we've used the universal quantifier there. Right? With a clarity that's not so clear to me when you're appealing to theorems of continuity. And then you just reason by equivalence, like you probably over-egg the pudding here, you don't need to do all that. You get the completely correct solution. And sure enough, the only thing that my system can't currently mark is, of course, this rhetoric in the middle. But already the interface has become very cluttered. This is what you would have to type in on the left as a student. It's not very nice, actually. So this is the big challenge, this interface. It's the big, big challenge. I think this sort of semi-automatic marking is very promising because it means the student who sends this to me to be marked knows it's not wrong. Whereas if they've made some algebraic slips, imagine this is an epsilon delta argument, part of an epsilon delta proof, they've got their epsilon delta proof wrong, they know that bit's wrong, I'm not even going to look at it until at least that bit's been automatically checked. Okay, so if we're being ultra pragmatic, as a middle ground, this kind of semi-automatic marking I think is going to be very useful. And it gets people into the habit of actually trying to formalise their arguments before they send them to a human to check. Yeah, you formalise the bits that can be formalised. So this is, I think, probably going to be quite useful. Although it means I have to go back to marking stuff again. Now, some people have said to me, Chris, well, why are you teaching them this algebra anyway? The computer algebra can do it. So what's the point of teaching it? Which is a good question. I mean, I didn't learn how to use a slide rule. Some people here will have learned how to use a slide rule, right? And log tables. No one bemoans the loss of those, do we? Really? So there will be stuff we just don't need to teach anymore, and I'm open to that suggestion. But from that premise that we don't need to teach this anymore, how are you going to get your computer algebra system to rewrite that inequality in that form? I mean, you have to issue commands to drive the bus, don't you? You have to tell it what to do. And we don't have an agreed vocabulary for telling the computer algebra what the commands are. As I've been here this week and looking at different people's automatic theorem provers, everybody calls things slightly different terms. Really, you know, just so that you still have to verbalise what you're trying to do, even if the computer does it for you. So I've got loads of design decisions. I've used HTML text area because it's just simple and free, and you can cut and paste one line to the other. So students don't have to continually tell them the same thing. I'll see how that goes. Should the students be expected to show any logic? Well, actually, yes, I think they should. Let me show you. I've got a if I just show you a blank thing, and you do x minus 1 times x plus 1 equals 0, x minus 1 equals 0. Now, if you miss a root, the system will say, well, if the second equation is true, then the first equation is true. So I do some kind of basic checking of that. Right? So, but shouldn't the students be putting that in? Well, maybe they should, but since none of my students put that in the actual trials with users, then I think that's probably a step too far. I don't know, we'll see. Should the students indicate what they've actually done at each line? Should they have a step-by-step, I did this to get from one line to another? Well, some people do write two-column proofs, and I think there's some real merit in that. Maybe they should. I might have some options in the interface in the future, and then semi-automatic marking I've mentioned. So that's back to Pell, isn't it, really? Working line by line, saying what you're doing, and doing it. Right, so I said I'm working over a variety, so I have to make some decisions about what you do about repeated roots. There are lots of wrinkles in elementary maths, actually, when you come down to try and do this. So my minimum viable product was being able to solve quadratic equations. I mean, there's really no point in releasing a piece of software for school algebra teaching if you can't solve quadratic equations. Right? That seems to be the minimum viable product. So I have to deal with repeated roots. So my current approach is to say that those are equivalent. So this equation is equivalent to that equation in my equivalence class, but to acknowledge that something has happened here, right? That we have missed a repeated root. Most computer algebra systems, and there are a variety of ways of dealing with this in computer algebra systems as to whether you return the same number twice, or you return a multiplicity for each root, or what you do. Okay. So that's what I've done here. Domains, of course. Which would you prefer? I've decided that that is not equivalent to that, and that I'm working over the complex numbers, that teachers will want an option. So if you signal to the students that you're really working over the real numbers, and this is the LaTeX output that my system produces, and I just cut and paste it into my slides, right? I mean, just to So it is equivalent if you're working over the real numbers. And then there are some very subtle differences, the things that I think elementary maths doesn't highlight very well. When you equate expressions, it's very different from dealing with equations. So this is part of, this is involved in Heron's formula. Right? And what you're doing is you've got some multivariable thing and you're saying that this thing is equal to this thing. And then you can do the difference of two squares. What have I factorised? I factorised, then you do the difference of two squares and you carry on. And this is what you need for Heron's formula to part of the proof.
I was going to ask you about this because I sort of was surprised not to see what you might call chain reasoning, which is
Yeah,
that
that's this, exactly this, yeah.
before the form that you showed us, which is this equation holds if and only if this one, if and only if this, because
Right.
chain reasoning somehow seems the first thing that people would think of as doing. I don't know whether you think that's true or not.
It is, but historically, it's not the way algebra's been taught in the distant past, because algebra is about solving equations. So if you go back to the 17th and 18th century algebra textbooks, they didn't have manipulation on their own. It's actually a fascinating story about how algebra teaching has changed. It was always equations. So in fact, if you look at all the elements of algebra, he doesn't include the factored form until he talks about the nature of roots of all polynomials. He's not interested in the factored form. He doesn't say factorise this quadratic and do lots of practice and then use it to solve equations. He solves equations by completing the square, and he only talks about the factored form later. So there are choices to be made about how we do all this. Now this has got some hidden universal quantifiers, and it's subtly different from working with a set of solutions. So here is a sort of minimal trivial example. These equations are equivalent because they have precisely the same solutions, but if we turn them into expressions by subtracting the 2 and subtracting the 1, then they're not, because they're not true for all values of the variables. Like, you have to work quite hard to find examples. This is perhaps, students will probably never encounter this example, and therefore never separate the concepts in their mind. But they are subtly different, so my system treats this chained reasoning differently from equational reasoning. And I want to be honest about the problems with my approach to dealing with the equivalence class of the solution set. And it's things like this. So there are sort of two options for this architecture. One is membership of an equivalence class, and the second is to deal with a sequence of legitimate steps. Right? Now the advantage of the former is that you don't have to define step size. The advantage of the latter is that you obviously can avoid these edge cases, which are particularly hard to write. Okay? So if you want to try and find other examples like this, good nonsense, fortunately, is hard to write. But I have to be honest, there are flaws with this sort of thing. Implication versus equivalence, so yeah, so this is the feedback that's given in my system. If you do that with the student work line by line, it will just say, well, you square both sides, so that's not an equivalence. These problems are out of fashion. They used to be in high school exams. And I spoke to a chief examiner of the A-levels exam board, the UK exam board, and she said they're no longer in A-levels because students found them hard. The reasoning was too hard. Yeah, right. So, if we've lost an opportunity to talk about these important things about reasoning. The problem is these equations have no applications that I can find. It's just a purely algebraic exercise. This isn't really the solution of any applied problem.
But what you're saying is that easiness is in fashion.
Well, yes, you could interpret it that way, I suppose. So my approach to all this is to start with this reasoning by equivalence and then progressively add more rules for feedback. So I have got a rule that decides that this is an implication, not an equivalence. So once you've established they're not equivalent, then you can start having a menu of things you can check. And in particular, one of the things that I'm developing is a pseudo-metric to judge step size. So as a teacher, practical teacher, I would like to say, well, I want to see a minimum number of steps and a maximum number of steps. No step should be bigger than this or smaller than this, actually, because trivial steps, there's an aesthetic to an argument. And perhaps even I don't want any of your steps to be so far away from my model solution. There's a whole range of things you can do with a pseudo-metric like this, but it's going to be hard to develop that. I've only started thinking about that, really. Yeah.
So I mean, the student who can just, thanks for your question, just see what the answer is because they have some kind of autistic ability to do mathematics is not going to fare very well.
Well, right, so that's interesting, because ultimately, I would sort of, with these quadratic equations, the goal of getting good at algebra is that so you can look at a quadratic equation that has integer coefficients, and you can do those things in your mind, and it becomes a single step. I mean, that is sort of the goal. That's why I think the step size approach to developing this kind of assessment system is going to be less flexible and less useful than the reasoning, the equivalence class. So it does depend. This is why I said you're responsible for your class. So if this is the first time you've seen this, you just want to get it right and end up in the right place. If this is a class which is a more advanced students, you would change the ground rules. And these ground rules change subtly in education all the time. So it's I'm glad you asked that. It's a really good question, and it's very important. But so if as a teacher you want to see the factor form, then you want to see the factor form. And of course, the advantage of having it automatically marked is you don't have to worry about condoning method marks or doing follow-through marking because the student has an opportunity to do it again if they get immediate feedback. So all those exam system things that we currently have could be changed. Rational expressions and roles of domains. So which of these is going to be, would you judge as correct? Well, I've decided that we would do that one. So this is what's working at the moment. Basically, polynomials are working, rational expressions are working. If you've never thought about this deeply, then I encourage you to decide the binding power of that relative to the other elementary operations. It's quite subtle. It took me a while to figure out. Maybe I'm slow, but it took me a while to figure that out.
Do you use the other one?
No, I haven't done the other one.
And the combination of the two?
Yes, and then what happens when you have what really goes wrong is Cardano's formula for the root of the cubic, where you have 2 plus or minuses in one expression. That's actually the killer case. So you see, this looks so elementary and trivial, doesn't it? But actually, just to get this working, you have
Cardano would be an SLP, it's not a formula.
No, that's right, and it doesn't work for complex coefficients. Is that what you're referring to?
Well, even over the real.
And I've got single variable inequalities over the reals. Well, modulo decidability of whether 2 numbers are the same. That's next.
Oh. Do they do modular arithmetic in school?
Not sure. That's next just because I need to release this for September. I mean, I've got stuff to do, so that is coming. It's mostly working, but there are some edge cases with absolute values that are not quite perfect yet, so I'm going to leave that to the next version. And maybe in the distance view trial I add some trigging, but the trig requires infinite solutions, and that becomes much more problematic, so I might do that. Yeah, so to what extent can we change this? Use of natural domains, multiplicity of roots, these are all difficult issues. If you want algebra to be a formal procedure and you want it to work, you have to change the rules of algebra as they're currently taught. So if you will have CA is CB, that is equivalent to A equals B or C equals 0. Right? Most people would ignore the C equals 0 bit. That was what led to the losing the root, the 10th root. Now, that was a mistake. There are situations where it's not a mistake. And the difficulty with this is that you have a formula here that possibly doesn't have C in it. There are alternative ones. You can have CA is CB and C is non-zero is equivalent to that. You still have to audit the fact that C is non-zero here. Other things, other rules, powers and roots are evil. I'll come on to that a bit more, but often you don't need to take the square root of both sides. You know, it's much better to take the difference of two squares and factorise. So this very famous book, Maxwell's Fallacies in Mathematics, has a lot of algebraical fallacies. It has some geometrical ones and some calculus ones as well. There's a lot of algebraical fallacies, and they mostly start off with, you know, A equals B, and then you end up with 1 equals 0 at the end. And if you use these kinds of rules, I wrote a paper on this, I went through Maxwell's fallacies with these rules, and actually all the fallacies disappear because it all goes into the auditing. If you audit it correctly, then there's nothing there. These rules take account of all these fallacies for the algebraic ones that we use. So it's not impossible to get this to work. And this is what students say about my system. Stack sometimes seems to have issues with answers that are essentially correct. Once I multiplied two square roots together, this was the example the student had typed in, square root of 3 minus x minus 3 times x minus 5, and it said my answer was incorrect. But then I did square root of x minus 3 times square root of x minus 5. That was correct. It wasted time because I thought my calculation must have been wrong and I was puzzled. So is this true? And he's in good company, he or she is in good company. I mean, there are these definition shifts in education. You start off with an inductive definition, you then go to extraction of roots, you have rational numbers, you have this very subtle real extension, complex extensions, and this is over like many, many years. It sort of creeps up on you through education. And the students that are confused are in very good company. That's not the contemporary view on how you multiply complex numbers. So when I didn't spot this the first time I read it, and eventually I went back to the original Russian edition to make sure it wasn't some typesetter's mistranscription. It's not. De Morgan does slightly better. Let the student always take the latter. But if you don't know the sign of A or B, it's not very helpful, is it? Right? So, and that's where I, the symbolism I, helps us avoid this trap. So I would say that is good at technological design. The I symbolism is good technology. It avoids this trap. So I've got lots of design decisions to make. I mean, I can give immediate feedback or not. I mean, students are probably not, for the time being, in the short term, going to want to type in domains. So my system does some domain checking. I can probably show you that somewhere. If we do, let's do this one. What was the example? Square root of x minus 3 times x minus 5 is equal to square root of x minus 3 times square root of x minus 5. Missing right bracket. Okay, thank you.
And also
The
the two should be a
that should be a 3 or the.
Yeah, right, whatever. Okay. But you get the thing. I mean, it does so. My system at the moment is indicating the natural domains, right? So at least the student has some sense as to why those might not be the same. But I'm not expecting the students to type in those natural domains because I just think that's too much for students. It's just too different from current practice. Whether we should change current practice, well, if people get used to this as an important issue, maybe they'll be more inclined to take it seriously. Yeah, okay, that's a good joke, really, isn't it? There have been lots of other similar systems, just as I round off. This is Michael Beesam's system. Anyone interested in education technology, I recommend his papers. This is from the 90s. And he wrote this system, and he's the only person in this area of online assessment who's taken the use of assumptions seriously and implemented something that does this sort of natural domain checking. Now, his system was very different from mine because in his system you would choose the expression and the system would give you a context-sensitive menu of things that you could possibly do to that expression. You would tell it which one you wanted to do, square both sides, and the system would then do it for you. And it would keep track of the domains, which, all right, it's learning how to drive the bus without worrying the details of what happens when you want to do something, which is fine. I know that's kind of useful. I want the students to do those things.
You don't ask them to say what they've done.
Not yet on mine, no. But Michael took the opposite approach. He only had them say what they were doing. This is a very popular high school system in France called A plus X, where the students work line by line and then they can backtrack, and it has some nice interface, so that's been very widely used. And just as a warning, this is the easy system for assessing proofs in Hoare logic. They got the difficult bit, and dispensed with the difficult bit in the title, because if you look at all the context-sensitive menus and rules and menus within menus and sliders and right, I mean, if you go down this route of trying to choose what you do and then do it, the interface just becomes horrible. So yes, this not requiring students to say what they're doing really simplifies the interface, which just to get going, I think is a reasonable thing to do. Right, these are key elementary concepts. I think we could use we could use this technique to solve a wider range of problems. I think that's probably not the most important issue. I think it's accepting that this is a thing and that we should value it and treat it carefully, which I don't think it is so much. Yeah, that's my third point. And in terms of pragmatic reasons, it's working, it will get used. I'm going to progressively develop this. There are lots of options for the interface, and this is not set in stone. I will trial this with students and we'll see what actually helps them. We'll do interviews with students as we've done over many years and find out what is really helpful. Can we change how algebra is taught? Well, we'll see. It's certainly an important opportunity to reflect on how algebra is taught. That was one of my original goals, right? If you can automate something, you have a better understanding of it, and I think that's one of the goals. So, thank you for your attention.
Chris, thanks so much for that. So is everything IB, RE accounted for a third of the marks?
Yep.
The only other statistic I know in that area comes from the Todai Robot project, which claims that 53% of their questions can be solved by synchronized rate decomposition. Which is interesting, yeah. Well, that's the problems are slightly different. Well, I'm not sure. Yeah.
Well, I mean, the important principle here is that we actually have some data.
Yes.
We look at what the students are really being asked to do, and we get some data on that.
Mm.
That's the.
Because this is what we're actually asking students to do. Never mind the curriculum, never mind the textbook, this is what we're asking them to do.
Yeah.
And as you also said, Chris, it's an enormous knock-on effect in what they do next.
Well, just reflect on the students you have. I mean, if they come to university, where are they actually tripping up?
Yeah.
And I find my undergraduate students are often tripping up on this kind of algebra stuff in first year.
So you talk a lot about assessment, but I think the most interesting part is learning. Can you use computer to help students learn quicker or learn better? Or
Assessment has a number of purposes. The first formative purpose is to help the student understand the subject, to help them learn. So it's a key part of learning. Summative assessment are the high stakes exams. That tends to be what drives priorities. And then finally you have assessments that check whether the curriculum is achieving its intended outcomes. So assessment just pervades the whole educational endeavour. So that's why I focus on assessment. So my system can be used in a formative setting. And that's how I primarily designed it. I didn't really want my system to be used for exams. In fact, the reason I studied IB exams was as an attempt to dissuade a colleague from using it for exams. I thought we'd be able to mark so little of the exams that it would demonstrate that this wasn't a suitable tool. Actually, with this extension to reasoning by equivalence, you can mark a lot more than I anticipated. So primarily the goal was to write a tool that will help students learn, formative assessment. But it's a tool, and if a teacher uses that tool, they're responsible for the way that tool is used and where it fits in all the other things you're doing as a teacher. It's got to be part of your whole coherent thing. So just like this maximum of 10 attempts business, you set those protocols in your course. So for the Open University who use my system, generally have 3 attempts. They have adult distance learners, and generally they fix the system so you only have 3 attempts. If you haven't got it right on the 3rd attempt, you should be talking to your tutor about it.
Do you have any overview of how these massive online courses are doing this sort of things? Like if you have tens of thousands of students, or I don't know how massive they are.
So Edinburgh is committed to these online courses, and I wrote one on statistics, contributed to one on statistics with Ruth King, who's the Thomas Bayes Chair of Statistics, and Mari Walker. She was a colleague in the Master of Edinburgh, and we had about 15,000 students sit that. And the platform that we used basically allowed us to do multiple choice questions only. Well, we can do better than that.
So an Untitled guy from the States, he had a very popular MOOC on calculus, and said that the part that was weakest was assessment.
Yeah,
He
that's right.
essentially was assessing, again, only multiple choice questions, which is an appalling way of assessing calculus.
I mean, multiple choice questions do have their place. There are some really well designed multiple choice questions that you have to understand something to answer correctly. But I think we need this technology as well to supplement that. We need to use all these things in the right places. Yeah.
Do you know about Educera?
Educera, I've heard of it. Yeah. I don't know the details of it, but
No, I don't know a lot of the details. So it's controlled, but it's controlled by a coach behind. So there are a set of problems. The checking is done by a proof assistant.
there are many, many other examples. I mean, there are commercial examples. Pearson textbooks and other publishers are producing textbooks. And there's a commercial publisher that uses my system to support their textbook. So you can buy access to the online course that they've written. That's fine. So if this is sort of going to become standard. It's already pretty standard. The first thing that I showed you where you assess the final answer, that's already pretty standard. Right, thanks for your interest.
Thank you very much.